telephone system can turn your voice into short flashes of laser light travelling along a strand of the world's purest glass. This glass thread, finer than a human hair, is called an optical fibre. British Telecom, together with others in the telecommunication industry, is using the application of science to rewire Britain. Glass cables are going under the ground, on overhead poles, and underwater. Soon, an optical link will join Britain with Europe. Light is just one part of the electromagnetic spectrum, which also includes radio waves. We're used to the idea of radio waves carrying speech and music, but light can do this too. This light-emitting diode, called an LED, is controlled by a sound amplifier. Together they make up a light transmitter. The light receiver is this photodiode with its own amplifier. Music from the cassette causes the LED to vary its brightness, variations that are picked up by the receiver and turned back into music. A prism can redirect the light. Optical fibre is the best way to conduct light signals. While LEDs, photodiodes and optical fibre are new, using light to send messages is not. The ancient Greeks flashed messages using their shields to reflect the sun. The arrival of the Spanish Armada was signalled by coastal bonfires. And during World War II, Aldis lamps were used at sea for Morse code. Light signals sent through the air have limited uses. You must have line of sight, which means short range. And of course, the light path can easily be interrupted. In the past, light has not been used for telecommunications, as there was no way to channel it across long distances. It can't be broadcast like radio waves, nor travel along metal wires like electricity. The invention of lasers in 1960 prompted scientists to start work on a cable to carry light. From the start, they knew they could send light down a short length of glass, because the physics of light reflection and light refraction would make the signal bounce along the glass. This experiment uses a ray box and a prism. Light travelling through glass into air at right angles is not bent at all. When the light source moves off the 90-degree angle, called the normal, we can see the ray, as it leaves the glass, being bent or refracted away from the normal. The angle of incidence of the ray increases, and eventually the refracted ray grazes along the surface of the glass. When this happens, the angle between the light ray and the normal is called the critical angle. Increasing the angle past the critical angle, the light stops being refracted and all the light is internally reflected. This is called total internal reflection, and only happens when light is travelling at an angle greater than the critical angle. Light that enters a glass rod always hits the edge of the rod at a greater angle than the critical angle. The light ray is internally reflected to the other side of the rod, where it's reflected back again. If you pick up a block of glass and look through it, you'll see that the inside walls form a perfect mirror. This is due to total internal reflection. Play with the length of optical fibre. It's easy to forget that light inside is still moving in straight lines. The reason is the light keeps on being internally reflected until it finally shines out at the other end. But while the theory works, To make a practical long-distance system is much harder. For one thing, the glass made in the 60s wasn't clear enough. If you look at an ordinary window pane, you'll see that edge on, the glass looks dark green. This is because of copper and iron impurities. A new manufacturing technique was developed to make a very pure glass, which is deposited from a mixture of gases. A glass so transparent that a wall of it, 20 kilometers thick, would be almost invisible. If the oceans were made of this glass, you'd be able to see right to the bottom of the deepest part. But even fibers made from this very pure glass are still not perfect. This glass rod behaves just like a giant optical fiber. Feed light into one end and it reappears at the other. Dimming the room light, you can see that the rod itself is glowing. Light is escaping across the whole surface of the glass. When we touch the glass, we destroy the refraction between glass and air.